Hannah, and I'm coming to you from the Arizona Science Center. For this week in our in-person and virtual camps, we are exploring the idea of surviving in space. So to start off this week, we're going to be talking about how to survive the super cold temperatures of space, and we're going to do that with our friend called liquid nitrogen over here. So if we didn't know this already, space is super cold, right? In fact, it is just slightly warmer than absolute zero. So it is at about negative 455 degrees Fahrenheit. Now, what is absolute zero? Well, what that refers to is the fact that substances on a molecular level, when they're heated up, the molecules, if you imagine my hands as molecules, tend to spread out and take more space and move more quickly. But when objects are cooled down, they start to take up less space. The molecules, they kind of get closer to each other and they slow down and they slow down. And then if they stop moving, that's what we call absolute zero. So again, outer space is just a little bit warmer than absolute zero. Now, we can't exactly simulate what it's like to be in outer space and the coldness of outer space here on Earth, but we can get close with liquid nitrogen. The reason is that liquid nitrogen is negative 321 degrees Fahrenheit, and actually we can't find liquid nitrogen naturally here on Earth. We have to create it in a lab. So we're going to use that today to explore how super cold temperatures affect some different materials. We're going to start by exploring and doing a little experiment with some balloons. So I'm going to make sure I have all my PPE on here, make sure I have my gloves. Now, if you do not handle liquid nitrogen properly, it can potentially burn you, but as long as you have insulated gloves on and eye protection and a lab coat, you should be good. All right, so I'm going to bring my canister of liquid nitrogen to the middle of my table here. First, I want to just kind of let you guys see what it looks like. Now, we can see that there's some vapor coming out of the container. Now, I'm going to take this ladle and just put a little bit in the speaker so you can see it. You might even also hear it. All right, so if you look closely at the speaker, what our liquid nitrogen is actually doing is it's boiling. Liquid nitrogen is so cold that it boils at room temperature. So what's happening is a state change, right? We're going from a liquid to a gas very quickly. And that's why we see all of that vapor. So I'm going to set that aside here. Now, for our first experiment, and you guys can make predictions about this, I'm going to take a series of balloons that I've prepared. And these balloons, they don't have helium in them. They just have, you know, the normal gases that make up our air in our atmosphere. Oh, that's being quite noisy over there. So, we're going to stick these balloons in there one by one. And right now, I want you to go ahead and make a prediction. You can even put it in the comments of the Facebook Live. What do you think is going to happen to the balloon? Do you think it's going to pop? Do you think it's going to get bigger? Do you think it's going to get smaller? So I'll give you a second to think about that if you want to share your predictions. And then one by one, I'm going to start sticking the balloons inside of our liquid nitrogen.
What do we think is going to happen?
Yeah, Megan, what do you predict?
Well, it's going to get really, really cold. I predict that it's going to maybe get brittle because the rubber when it gets cold might not be as stretchy.
Awesome.
That's my thought.
Well, let's go ahead and give it a try. So, first balloon going in. Oh, you know, I might have made these too big.
Uh-oh.
Darn it. Okay. Let's see if I can fit one of them in here.
There was a smaller one.
Oh, squeeze it in. Okay. Ah, darn it. All right. Here. I'm going to hold it a little longer just to see if I can change its size based on what's happening and get it to fit in there.
Tansy says she thinks the balloons are going to fly away.
I have another alternative too. Yeah, I just made them. These balloons are too fat to fit in here. Okay, second plan. All right, Megan, if you want to step back just a little bit.
All right.
We'll just show it this way. So instead, I'm going to pour some liquid nitrogen over my balloon here.
Sharon thinks the balloon will freeze and deflate.
All right, let's check it out. So instead, I'm going to pour some liquid nitrogen over my balloon. All right, and then Miss Megan, if you want to zoom in a little bit closer now, let's check out what happened to our balloon. Let's do it one more time. I'm going to pour a little bit more on my balloon here. You should be good to come closer now.
Oh, wow.
All right, so as we can see, the super cold of the liquid nitrogen, just like we talked about with our molecules, it actually makes our air molecules stop moving. They slow down and they get closer together, which is why the balloon shrinks. Then, very quickly as well, when the balloon starts warming up and getting to room temperature again, it starts expanding again and gets pretty much to normal.
Nice.
So, that is what happens to air when we expose it to super cool temperatures, right? The molecules, they get closer together and they move more slowly. Well, let's try out a different material, a different substance. Next, we're going to try a water balloon. Okay, so this one will definitely fit. I'm going to stick this one in here, and while we're waiting, we're going to listen for a sound. Let me give you a hint. We're going to listen for a sound coming from this canister here. We might not hear it, but while we're waiting for our water balloon, let's talk a little bit about the special properties of water. So water is one of the very few liquids that actually expands when it freezes. Most liquids shrink. Like we talked about, most molecules, when they get cool, they take up less space and they move around a little more slowly. But with water, it expands when it becomes ice. And we've probably seen this if we ever have had a water bottle that we stick in the fridge and it kind of explodes or it expands a little bit. So we're going to see if we find that with our water balloon. Now it's probably going to take about 30 seconds longer. Oh, I heard a noise. I don't know if you guys heard that, but I heard kind of like a popping noise. Make a prediction. What was that popping noise? What do we think happened? Okay, and I'm going to go ahead and take our water balloon out.
Ooh, lots of lights.
I have a couple of goodies in here, so I have to find it. Oh, here we go. All right,
Oh,
check
wow.
it out. So because our water expanded so quickly, it actually expanded so much that it broke our our balloon material. Also, the rubber of the balloon material gets more brittle or breakable when it is in some super cold environments. So as we can see, our balloon is just a solid ice now, and it actually broke open that balloon. Pretty cool. So we have now tested a gas, air, under super cold temperatures. We have tested a liquid, water, under super cold temperatures. Before we move on, I want you to think about, if water freezes like this in super cold temperatures, what kind of problems does that pose for astronauts, right? We have to be able to transport water to the International Space Station for the astronauts to survive there. So be thinking about some ways that they could maybe do that. All right, next, we're going to try some solid materials. So before our Facebook Live even started, I put some solid objects inside of our liquid nitrogen. We're going to start by pulling out the orange. Oh, this is actually super exciting. Our orange did something actually comparable to our water balloon that we're going to get to talk about. So this was just a normal orange when I put it in, but guess what? Check this out. The orange cracked open too.
Wow.
Put in the comments, why do you think the orange cracked open too? How does the orange relate to our water balloon here? Well, if you think about the content of fruits, there's a lot of water in fruits, right? So again, that caused the outside or the skin of the orange, there was just too much pressure from the orange's skin. Pretty cool. All right, next we're going to move on to, I have a racquetball, okay? So first, let's demonstrate actually how a normal racquetball works. Now, if you've ever played racquetball before, you know that the ball has to be very bouncy, right? It's made of mostly rubber, has to bounce off the walls. So what we're going to do is I'm going to drop a normal racquetball in room temperature and our racquetball that's been sitting in the liquid nitrogen from this distance onto the tile floor at the same time. Make a prediction about what you think might happen. How is the super cold racquetball going to perform as opposed to our normal racquetball? Okay. All right, we're going to go for it. All right, in 3, 2, and 1.
Oh.
Check it out. Okay, thank you, Megan. So our super cold racquetball shattered into pieces. The reason for that is that the rubber material lost some of its elasticity as those molecules got closer together and slowed down, it became more brittle or easily breakable. And that is why our racquetball shattered. Next, we're going to try a bouncy ball. Let me fish this normal one out here. Okay, so same kind of concept, but smaller. This is a normal bouncy ball. Okay, I'm going to drop my normal bouncy ball and my very, very cold bouncy ball at the same time. And go ahead and make another prediction. Do you think the same thing's going to happen with the bouncy balls as the racket balls? Why or why not?
Looks
Okay.
like Kennedy Ann did predict that was going to shatter.
Awesome.
So,
all right, let's
very
try
nice.
the bouncy ball. So again, this is the one that's been sitting in the liquid nitrogen, and this is my normal bouncy ball. Okay, so the bouncy ball didn't shatter this time, but you might have noticed that it lost some of its bounce, right? So again, the material lost some of its elasticity when it was super cold. Think about how that might affect when we're engineering spacecraft and things that we're sending into space. We need to think about the properties of materials and how a super cold environment is going to affect them. All right, so the next thing I'd like to talk about is, we've explored how super cold environments may affect different kinds of materials, right? We tried out some air from the air in the balloon. We tried out some water, which was our liquid, and then we tried out some solids to see how it would affect those. But how do astronauts protect themselves from the cold of space? Well, the general idea is to simulate an Earth-like environment. The International Space Station has a thermal regulation system that keeps the astronauts comfortable at all times. And that's important because depending on what side of the International Space Station you're on, whether you're facing the sun or not, that can really drastically change the temperature that you'll experience unless you have that thermal regulation system. Now in spacesuits, there is kind of a pressurized atmosphere inside the spacesuit. That's why they look kind of balloon-like. And that prevents the liquids in our body from boiling or freezing. We probably don't want that. Also, there are layers of different insulating materials, such as mylar, such as Dacron, such as Kevlar, and Kevlar is anti-tear as well. And I brought an example of one of those materials to my call today. This is a mylar blanket, all right? So you might have seen these if you've ever run a marathon before. So these are what people hand out to marathon runners when they finish the marathon. The reason is that those people might experience a drastic change in body temperature, which is not good for them. So what this blanket does is prevent that. And part of that is because of its reflective surface. And also spacesuits have that reflective surface to control the amount of change in temperature that might result from the temperature or the light from the sun. All right. Okay. So we've talked about how different materials act in different super cold environments. We've talked about how we can protect ourselves from those super cold environments. I want to end our Facebook Live talking about, well, where can we find liquid nitrogen in actual nature, in our solar system? Well, if we go out past the asteroid belt, all the way to Triton, which is a moon of Neptune, we actually, with the Voyager 2 spacecraft, have found evidence of ice volcanoes. Now, these ice volcanoes, they spew out a mixture of liquid nitrogen, ice, methane, and dust. Now, for our finale today, we're going to actually simulate an ice volcano right here at the Science Center. To get to that, though, I want to do one more demonstration first. So this one is going to kind of explore the building up of pressure. So I have this can here, all right? I'm going to take the lid off. I'm going to put a little bit of liquid nitrogen in the can, and then I'm going to go ahead and put the lid on. Go ahead and make a prediction now. What do you think might happen? All right. Remember that liquid nitrogen is going through a state change. It's going from liquid, and it's insulated in this container, so it's liquid, but as soon as it meets room temperature, it's going to start doing a state change into nitrogen as a gas. So let me open this up, and I'm going to go ahead and stick my liquid nitrogen in my container here and put on the lid. A little bit more. Okay. Make your predictions now. Here we go. Oh! Let's try that again. Why did that happen? on. Let's try it one more time. I'm gonna really try to get on there. Oh,
Yeah.
okay. Oh, it took longer that time, but it still popped off. Why did it pop off? Well, as our liquid nitrogen is becoming nitrogen gas, again, the molecules as they're warming up and becoming that gas, they're taking up more space, and that builds up pressure inside the container, which eventually pops the top off. Now, this is going to relate to our final demonstration. So, we're going to be using some different tools, but similar concepts. So, I have an Erlenmeyer flask here, and I have this interesting stopper that has basically a metal straw through it, okay? So what I'm going to do, and we'll probably do this twice, I'm going to put some liquid nitrogen at the bottom of my flask, okay? Imagine that's, for example, the liquid nitrogen inside of those ice volcanoes on Triton. And then I'm going to put the stopper on. Now, just like putting the cap on my canister here, built up the pressure and then it popped off, well, I'm going to put a stopper on my flask. But the difference is that I have a way for that pressure to escape through this straw, and we'll see the effects. So I just recommend you guys keep your eyes peeled on this because it happens quickly. Now, unlike the geysers and the ice volcanoes on Triton, I'm not going to shoot this straight up because that would not be very safe for me or for Miss Megan. So instead, I'm going to shoot it this direction, all right? Okay. I'm going to put a good amount of it in here. Now, these geysers on Triton can actually shoot up to 5 miles high.
Wow.
And then, at a certain distance above Triton, they start to drift, and they can drift up to 87 miles. Pretty crazy. All right, let's do one more scoop here. All right, I'm going to go for it in this direction. Ready? 3, 2, and...
Whoa.
All right, let's do that one more time. Like I said, it happens quickly.
And Miss Hannah, I noticed that those giant gloves you're wearing are definitely protecting your hands while you're doing
Yes,
this.
for sure. They are insulated cryo gloves. All right. Let's put a lot in this time.
Now, I know Miss Hannah has gone through special training to be able to handle liquid nitrogen. It's not something that you can just play with at home.
Very true.
You have to be extra careful.
All
right, here we go.
3, 2, and 1. Oh, yeah. All right, everybody. That is it for today. I would love for you guys to join me for the next Facebook Live tomorrow at 12:30. I will be with you again talking about moonquakes, because believe it or not, there are earthquakes on the moon, and we're going to talk about how we can design structures if we ever potentially had a colony on the moon or another space object, how we could prevent those buildings from falling during an earthquake or a moonquake. All right, everybody, if you want more hands-on science activities, definitely check out azscience.org, and I will see you guys tomorrow. Thanks for joining me.